Andrew Uselton has been with DOE Labs for 15 years and with NERSC for 6. His involvement with Lustre goes back to its beginning. He has a long history of modeling, analyzing workload of HPC systems that use Lustre. Andrew lives in the San Francisco Bay Area. In July, Andrew will be joining the Intel High Performance Data Division as a performance engineer.
So we have a little
Uselton.
Yes. So we have a little bait and switch here. I think the program says something about a file system utilization metric, but I'm actually talking about balanced design. They're actually the same topic. The file system utilization content that I have in these slides is also going to be at CUG, so I'm going to, in the interest of time, bounce through them really quickly, and I hope that I'll get across sort of the main ideas without actually dwelling on it. And definitely stop me in my tracks when you catch me lying, because questions in the middle of the talk are most welcome. So the purpose of this talk is to take some of the workload characterization stuff that I'll be talking about at CUG and carry it even one step further. And the one step further, the context for all this is I really want to answer the question, if I've got this budget and I have to carve it up, some of it goes to compute, some of it goes to I/O, where do I cut? You know, where's that balance point? And then the first bullet point determining the workload is most of the slides here, and that is the same thing that I'll be presenting at CUG. And then the last 3 bullets are going to be about 3 slides where I sort of tell you how I'm going to go about trying to tell you where that balance point is, and if we're quick, and Steve is nice, we might actually get there. So all of this work is using the Hopper Cray XE6 as a test platform, and that is, it's been around since 2010. It's got a bunch of cores and a lot of memory and cool door art, which I think is very important. This is what Hopper looks like. I think all of you understand that. That you understand about OSTs, and the Lustre monitoring tool is just something that's off the cluster, and it's a database collecting information. The kind of information you're getting is how many bytes were read, how many bytes were written, but we're also interested in that channel down at the bottom, the actual OSS talking to the RAID arrays. So this is what LNT data looks like. Time is on the x-axis, megabytes per second is on the y-axis, red is for reads, blue is for writes. On the left, you see a day that was didn't have a lot of I/O. The average there was well below a gigabyte a second. And on the right, you see a day that looks like it must have been pretty busy. If you look at how much data was moved in a particular day, you can get these histograms over the course of the year. I think I'm going to skip on past this. This is the pickup curve or transfer curve for if you do I/Os with a certain size, then what is the best rate you can get? And this is out of one OST on Hopper. Or perhaps like this may actually be for the test system Grace, but similarly constructed. And the idea here is that we all know that when you do small non-sequential I/Os, that really tanks your performance. And so all I'm doing is documenting that effect. Now, I have extended the LMT with a new module so that I'm actually collecting the BRW_stats information. That's a bunch of histograms about disk I/O performance, RPC sizes, that sort of thing. I'm going to use that to put it together with that transfer curve so that now I actually know how many of my I/Os are tiny I/Os, and I can then tell you for a particular pattern of I/O what is the best rate you could expect. So this is the gathering of the data over, 4 months or something like that. And you've got 9 bins from 4K on the left to 1 megabyte on the right, and these are the disk I/Os. How many of them were there? So the count is on the y-axis. And as you can see, it's a bimodal distribution. Almost all of the I/Os that are not at that optimum 1 megabyte are all the worst possible case. So there are some that are in the middle, but basically you only want to have these 1 megabyte I/Os, and anytime you're not 1 megabyte I/Os, you're killing your performance. So then this is just a pie diagram showing, 60-40, how many of the I/Os were good and how many were bad. If you go back and actually use the disk I/O statistics to calculate what fraction of the data rate you'd expect to be able to get at the best versus what data rate you're actually seeing, Then this is those same 2 days, and now the day on the left, the black gives you what I'm calling the file system utilization. This is what fraction of your total capacity for doing I/O were you using on that day. And of course, on the right, you knew that you had a really busy day, but on the left, it's actually a really busy day too. You just didn't know that until today. So then how often does it happen? This is a histogram of all the samples, 17,000 samples a day over 120 days. Just put them on a histogram. The first bin is up to about 2% of your capability. Anytime you get above a value of around 30, the file system is actually running almost flat out. The flaws in how I calculate the file system utilization make it so that it's not a true percent utilization. That is, if you could only go up to 100, and if you're below 100, you still have that last 10% available. Basically, with this statistic, anytime you get up above 30, you probably don't have much, if anything, left on your file system. So then this is a pie chart breaking out those same things. The blue is for that first bin, 2%. The red is for when you're above that cutoff of 30. And then the green is anything in between. And then you can also, for each of those pie slices, you can then go back and say, well, for that pie slice, when it was really busy, what was the breakdown between good IOs, the 1 megabyte IOs, and how many of them were the little IOs? And that's these 3 little pie charts. So when Hopper Scratch is running flat out, 3/4 of the time, it's with small IOs. So that means that if you just use bandwidth that you see from LMT as your proxy for the load on your system, you're missing 3/4 of the load on your system. So that's the main result you should get out of all this. So now I'm going to go into that cost model. I'm going to go into how do you determine balance. And again, for the sake of time, how am I doing for time?
How many slides do you have?
It's like 3 more slides.
Okay, then you can slow down. No, I was like the 20-minute slot, and I looked at the number of slides.
And we started, I think, about the time I was supposed to be finished.
No, it was incredible, though, Ben. You've been sprinting, and it's like, look, man, here, have some water.
Well, and it's a big snow job, too. I mean, there are a lot of things in there that you should be going, no, wait a minute, you were lying to me about this. So, we can definitely go back. Okay, so here's the thesis. I'm going to take these 4 statements about how I/O purchasing committees do I/O. So you're going to take your budget for I/O and you're splitting it into 2 pieces. One is called I/O, the rest is called compute. I'm going to tell you that when you're computing, you're creating an amount, a workload that needs to be communicated to the file system at a steady rate. So however long you're computing, that's going to determine how much I/O you have to do. And then when you have to actually do that I/O, you stop computing. And so obviously if you don't have very much I/O, then you can, if the I/O rate production is very low, then you can mostly compute and just a little bit of I/O. If your I/O production of your compute is very high, then you're going to compute for a little while, and then you're going to have to spend a lot of time doing your I/O. So that's the trade-off in that third bullet there. And then and then I guess, these statements, basically I wanted to put these in words, but you can actually also turn these into a system of equations. You can solve those equations analytically, and it will get you some curve that looks like this, where on the x-axis we have what is the fraction I spent on my compute. So the Hopper, we spent about 90% on compute and about the last 10% on I/O, and that may not be the exact right number, but that's what I had heard. On the y-axis, I'm basically calibrating this whole model in amount of science you get per dollar spent, basically. So the science you get per dollar spent will be 0 if you spend no money on compute, right? That's all the way on the left. And it'll be 0 if you spend no money on I/O because you did all these great computations, then you threw it away unused because you can't save it anywhere. Somewhere in the middle, you get a max. This is an analytic curve that I actually derived from those equations. So what do you do with an analytic curve that has a maximum in it? You take the derivative and set it equal to 0. I've also used the results from the early part of this presentation on Hopper to actually calibrate this. So this is actually the curve for Hopper if you believe all the lies I've told you. So the blue line is just the derivative of the black line, so it goes through 0 right there at about 0.83. You can, when you take the derivative, set it equal to 0, and solve for the value of f sub c on the x-axis, that is the fraction of compute that would be at the max, you can actually get an analytic solution for that. And so you get an analytic solution for where that red dotted line goes, that's going right straight through the peak. And for the calibration of this curve, based on Hopper, if you believe all of my lies, that peak says we should have actually spent about 17% on I/O instead of 10%. Let's see if there's anything else I want to say. Oh yes, the one other cool thing, and this is strictly, just the mathematicians in the audience will go, oh cool. It turns out when you're at the peak, the fraction that you spend on compute, which is the big F sub c, is actually equal to what I'm calling little f sub s, which is the fraction of time you spend doing I/O. So, or the fraction of time you're doing science. So if what this says is if we had designed this just right, we'd have been getting the maximum science done if we did science for compute for about 83% of the time and did I/O for 17% of the time. So the fraction that you're spending needs to match the fraction that you're actually computing, which I don't know that there's any necessary reason why that should be. It falls out of the equation. I just think it's cool. If you go back to the equations and you find all the little architectural parameters that went into it, you gather them all up. It's the unit price of a node, it's the unit price of the price of a unit of bandwidth, which is just how much does it cost to get 1 gigabyte per second or whatever. How much science you get done per node, per unit time, and then how quickly will a unit of I/O drain away the I/O that you need to do. And you put those all together, they actually appear in one place in the analytic solution as this expression, which I just then called gamma. You can then take, this is the curve for Hopper. You can say and so now if you look at, gamma is now plotted on the x-axis, and so where you see the 1.0 for gamma, that is basically saying, okay, we did Hopper. If you go up, you see, okay, the maximum is 83%. If you then say, well, I don't really believe your workload characterization, I think you're overstating it by a factor of 2. Well, okay, go look at gamma equals 0.5. And that will tell you, if you really think I overestimated the workload on Hopper by a factor of 2, then that tells you that you really should have spent maybe, closer to that 90% that Hopper did in fact do. You could also use this in another way. You can say, well, for my next procurement, the I/O stuff is really going to cost about the same as it ever cost. The disks are not getting that much cheaper that quickly. The other aspects in the parameters that went into gamma, they're all going to be the same with the one exception, is that we're following Moore's law, and the productivity of my node is going up by a factor of, let's say it's 3 years before I bought my next one, so I now I've got a compute node that can do 4 times as much. Well, that means gamma is now 4 because it's actually linear in that parameter. So that means that you now need to, based on this, if your workload on that new system were identical to Hopper and I've calibrated it correctly, then you should be spending something like 76% on your compute, and what would that be, 24% on your I/O. That's what this gamma curve is telling you. So that's it.